All right. Hey, everyone. Nice to see everyone here. Hope everyone's having a good morning. So I'm going to talk about Relay. So TNG just gave a little bit high-level overview of the stack. The morning is sort of organized as a layer-wise stepping down the stack until we get to hardware, and then the afternoon is sort of more focused on applications and use cases of TVM as a whole. So first, I'm going to do a little motivation too. I think one of the challenges that we're trying to solve here, and you might ask, well, what are these levels of the stack? Why do I care about the levels of the stack? And what do the pieces fit into, say, if I'm doing hardware development or if I want to write an optimization? So kind of the old history of deep learning is that we started in Wild Wild West where people were writing code in MATLAB. Occasionally, we write in a weird language like Python or C. And this was what machine learning was like back in the 2000s. Then there was sort of the first wave of people using hardware acceleration. For example, frameworks like Theano and Torch allowed people to utilize GPUs to accelerate their programs. Around the same time as when we saw deep learning really come on the scene, and people were demanding more data and more compute than ever. And then we saw the frameworks that TNG just talked about for a few minutes all kind of come into the view as people built these systems that provided parallelism and distribution and all these other nice benefits at the systems programming level. The challenge is like, how do we move? One challenge is sort of how do we move forward, because this is not really the full history of what's going on either. At the same time, there's been this explosion of accelerators. All the big companies are manufacturing them. There's also an explosion of compilers, and these might all look like blocks that you can plug and play that are built really nicely to compose. But currently in the world that we live in, if I wanted to build the next solution, for example, this thing out in the future, how do I get there? Because realistically, these stacks are far more like verticals. So for example, TensorFlow and XLA are very tightly designed and integrated, and they have black box support for the GPU, for example. PyTorch has Glow and some other compiler efforts internally to support a variety of hardware devices. And then MXNet, people are mainly using TVM, and they're also building their own hardware. And I think the question becomes, even as you see a proliferation, I skipped too far ahead, a proliferation, you see these things like TensorFlow Lite, where TensorFlow Lite actually has its own graph definition with its own semantics, and it supports a limited set of devices. And so now if you're out there and you're like, hey, I just want to take a high-level model, or all the high-level models that are out there today, get them on my hardware device, where do I start? Because TNG talked very much about the operator level this morning, but an operator is not a neural network. It is just a matrix multiplication or a convolution. So we really do need to optimize the whole program, especially as models start to become more and more complicated. So really the question is, how do we build a bridge to the next generation of systems that we're trying to answer when we started to do this relay work of how do we enable sort of decoupling the programming model from execution and allow people to transform general purpose programs down to the devices they want to support. So in general, the challenges that we tackled here in this work is how do we represent complex models? So in NLP space and in reinforcement learning and a lot of these other domains that people are working in, there's a huge number of models that are now very complex, very dynamic. They have arbitrary allocation, they have control flow, they have iteration or recursion, they have data types sometimes. And you can write all of these in PyTorch, say, today, but the problem is PyTorch is a Python program. A lot of the code actually executes in the Python interpreter. How do I get that on my devices? For example, how do I deploy it to my mobile phone? Especially as we see this large number of accelerators coming out. So really the questions we answer in this work, and I'm going to show you, is building a sort of a stable abstraction that allows people to build new languages, build a new framework. How do I, say, design a new optimization or support a new architecture? So in order to do this, we've put another layer inside of TVM, Relay. Relay is designed to be a high-level, extensible, intermediate representation in TVM. And the goal is that we want to adapt to this. We need to be able to flexibly adapt to all of the changes going on in the ecosystem. For example, a few years ago, no one cared about Transformer. It wasn't even out yet. And now it's this cutting-edge workload that people care about a lot. And we've seen many generations of this. And sort of TNG touched on this a little bit this morning, but right now, you're able to get good performance in certain models due to a lot of hand optimization by a large number of engineers. But as a researcher, sometimes my interest in a model might be stymied by the fact that I can't get it to perform very well. And so I'll just abandon a line of research. So how do we kind of prevent that from happening and allow people to leverage performance when they're doing non-traditional things? And I'm going to talk a little bit about Relay over the next couple slides. So you can imagine we obviously have looked at other compiler infrastructure in the past. So LVM pitches itself as a collection of modular and reusable compiler and toolchain technologies. TVM, when it first began, was very focused at the operator level and has continued to grow into more of a tool chain. But I think you can really apply this to us today, too, and we could borrow pretty much the same words. We want to be an extensible, modular, and hackable infrastructure for building tools and languages for deep learning. In order to do that, we felt that we needed a high-level way to represent all of the models that people are running today. So my talk is mostly going to focus just on this top slice of the stack, and I'm going to talk about how we represent models in Relay, and then how we use the operator infrastructure that TNC just talked about to compile them efficiently to a variety of devices. So one of the key questions in designing an IR like this is, what do we need for deep learning? So if you want a general purpose programming language, you think very differently because you want to operate over scalars, and you want arbitrary loops, and you probably want mutation, and a lot of other language features. And in deep learning, the main things we need is a representation of computation, which has often been computation graphs in the past. We need a way and a mechanism to differentiate that computation, and we need some optimizer to optimize it for training purposes. So the existing approach today sort of is that you can see these solid arrows on the top. ResNet, which is a completely static model, a fixed number of layers, you know the dimensions at every layer. It's really easy to represent as a computation graph. It's very easy to optimize down to target platforms. The problem becomes when you have something like an LSTM, you have something like a training loop, which contains loops, maybe some other kind of dynamism. You can represent these in the frameworks today, but the way that they're often implemented, say in LSTM, someone writes a CUDA kernel that does a fixed unrolling of the LSTM and then executes it efficiently on the GPU. The problem becomes, what happens if I want to change the LSTM's primitive time step? How do I do that? Well, you could add a new operator to TensorFlow or PyTorch, but that requires you to fork the code, make a modification to the CUDA kernel, re-export a new operator in the framework, rewrite your model, and then it only works in the GPU. What happens when I have a hardware accelerator? What happens when I have a CPU? What happens when I have a new device like RISC-V or some other things that people in the TVM framework have been working on? So our goal here really is we want to be able to pull all the computation down into our IR, even if we can't necessarily run all of it. For example, if I'm on a microcontroller, I might not be able to run certain models, but I want to at least be able to represent them and not reject you at the first level of the software, because sometimes just by doing a little bit of optimization, I'm able to map down computation to the device that I might not otherwise have been able to. So really our goal, like I said, is to represent it all. So a couple details about Relay. So the goal for us was that computation graphs are a really limited programming model. People, at first, they're essentially just function calls that can take arguments, and they can produce multiple outputs. People have made some hacks to add control edges. Then you're like, well, I want a data structure. So for example, TensorFlow has like 2 or 3 primitive data structures. But if you want a different data structure, you're out of luck. If you want a different kind of control flow than the looping constructs that they provide, you're also out of luck. So the question is like, how do we build something that can be extended and also represent the whole program? In order to do this, we built a lot of infrastructure. So there's a new intermediate representation, the AST and the format itself. There's an auto differentiation algorithm, which I'm not going to talk about today, a program optimizer, not a machine learning optimizer, and a variety of hardware backends. So the IR is inspired a lot by thoughts we've done in optimizing data parallel functional languages, in writing functional compilers, and thinking about what's easy to optimize and what's easy to represent, as well as thinking about what people like about computation graphs. So one of the main advantages of the computation graph DSL that everyone's used is this pure data flow. So thinking about optimizations is very easy for most people. The problem is if you make these ad hoc extensions, that fabric of it's become sort of a fabrication because you have a control edge, if you have mutation, if you have loops, it's not really data flow anymore, and you have to start to think about transforming it in very different ways. So in order to solve this challenge, we have a language that has closures, mutable memory in the form of references, data types, primitive operators such as convolution or matrix multiplication, which are backed by TVM, as well as tensor values and control flow. And I'm going to talk a little bit about it in the next slides. And so what we can do is we can still have a subset of the language that we can optimize like people have been optimizing computation graphs, but we can actually represent more and optimize more. We also have a type system which tracks static shape information. So the previous type systems that people have designed for computation graphs have been like a post facto shape analysis. So they will take a computation graph and try to propagate shape information over it. This works really well, again, when you're in a data flow setting because it's not very hard. For example, if I have a function call, it has some shape arguments, and its output is a function of its input, I just run a function that computes its output shape. This is very much how TensorFlow works or MXNet today. The challenge is now if I have control flow, if I have recursion, how do I represent these things? Especially when my primitive types now no longer just contain tensors, but maybe recursive trees or lists, so on and so forth. So I'm going to show a quick example, and then I'm going to dive in a few minutes into our notebook. So for example, I want to take an RNN, so I've unrolled an RNN in time here. The idea is that I take in an input every step, and I take in a hidden state, and I produce an output in a hidden state, and I just keep feeding it in. The challenge, like I was saying in a previous slide, of representing recursive neural networks like this often today is that you can see this core chunk of the cell maybe. So the cell will implement like the operation at one time step. the cell will be accelerated in some of the frameworks. So for example, if you write a program like this in PyTorch today, where you want to use a primitive cell and you want to loop this in Python, the only code that's going to be very fast and running on the GPU, for example, will be the stuff in purple. And the outer loop will have to execute in the Python interpreter. So you can kind of think of this metaphor as a control data plane sort of metaphor where you configure the operations you want to do, you push them to the GPU. If you want to make a control decision, you flow back to the host device, make the decision in the Python interpreter, reconfigure the GPU, run it again, and do this in a loop. So what we'd like to do, especially if you're thinking about targeting, say, an accelerator where you don't want to host a device in a loop, we can just increase or attempt to increase the coverage of the entire language, and this is what we're going to do in Relay right now. So you can see we have this is kind of what the IR looks like. So here's our textual format. At the top level, we have a linear layer, for example, and I've omitted the types here because they're inferred. You can imagine now here at the bottom, we have a declaration of an LSTM cell, which I've omitted its implementation because it's pretty lengthy. It's a couple slides worth of text. And then I just want to do a simple encoder. All it's going to do is take an input, map it into the hidden representation, and then give me a vector of all the inputs in the hidden representation and the final hidden state. So in previous frameworks, you'd often write a big blob of CUDA code to do this. You might not have any data structures. So what we can do is we can just define a functional list, and this is something people in programming languages do all the time. And this is not necessarily the best way, but it's just one way to do this. So a list here is either an empty list, or I can put an element on the front, and I can build this up. And so this is like a linked list in memory. Then I can define, sorry, just one more slide. So cool, these things support all kinds of fancy data types. They also have polymorphism and can be recursive. So it allows us to really write all the kinds of data structures we want. One thing we can do, for example, with these, though, is actually just partially evaluate most of them away at compile time. So oftentimes these are not necessarily even need to be compiled to the device, but they allow us to represent programs that do things that are more sophisticated. We can define a full, for example. This is a reduction operation in place of a loop. So I think the goal of showing you this is that we can implement new reduction strategies or new iteration strategies over data structures. So in this case, it's going to take a function, apply it to each element, and then accumulate the result. So if we go one slide away, forward, right? So this is a traditional fold. We're just going to accumulate a result. So it's like a loop with a little bit of state. We can then define an encoder in our IR. So this is like the most general version of it, where we have some type variables at the top. So we can take an arbitrary cell, we can take an input, and we can take a stepper function, or sorry, an input and an initial state. We're going to define this step function here. So the idea here is this is actually doing the accumulation. So we can have something that at each time step is going to get out the previous hidden state, the list of outputs that we're building. We can then run the cell for one time step. We'll get out a new hidden state. We'll get out a single output. And then we're going to pass on the new hidden state and the list of outputs that we've been building. And then with this, we've defined an encoder. All we do is call it, and we're done. And so we can now encode a loop just like this by just translating it to this fragment of IR. You might ask why we don't directly use loops. One of the challenges that happens is if you allow people to write arbitrary loop nests, your ability to optimize the program becomes severely limited because you have to do very sophisticated program analysis. So this is a challenge that I think a lot of these DSLs and languages are facing is, like, for example, in CUDA, you are writing full C++. Optimizing the program is really challenging. You take a TVM model where you have a really concise representation of the loop nest. It's very easy to optimize, and we want to extend that to the graph level in these compiler frameworks as well. So once we have this, we can take a relay program like the one I just showed you. We can extract all of the operations out of it. So for example, because we have an LSTM, there's probably an add, there's a TANH, there's a bunch of other operations. Then we can generate tensor IR, what TNC just showed in the previous talk. And then we can do the same process that we were just talking about. So when we're done compiling these tensor expressions, we'll get a shared library that contains function pointers implemented in destination passing style. So they expect all their input and output buffers to be allocated. They can then be called by a higher level program. And then our compiler will emit the code for the rest of the higher level program. So you can see, just a reminder what TNC just showed you. You can do this existing approach. Everyone maps their operations. So you take a high level program like the one I just showed you. For every primitive operation, you find a corresponding operation in a device library provided by your GPU manufacturer or maybe your CPU manufacturer. Sometimes, though, this approach fails today, for example, because CPU operations are often left unimplemented. So if you just want to even test your model on your laptop sometimes, you might have trouble doing that. And then someone hand engineers the code right now, like TNG was showing a few slides ago. And then, but what we can do is, because we have this high-level representation, we can take the operators written in your relay program. So you give us a high-level model, maybe imported from TensorFlow, from MXNet, from PyTorch, and we can apply all the optimizations Tianqi just showed. So we can do loop tiling, we can map to accelerators, so on and so forth. And with that, I'm going to just wrap up and show you the notebook. So what I'm going to do next is we prepared some interactive materials. We have everything running in the cloud. You guys can open an IPython notebook, and I'll direct everyone through it in a second. And we can step through some code and examples and stuff. So with that, I just want to remind our goal is to abstract over hardware platforms and low-level engineering details so that people don't have to constantly do these graph mapping optimizations, many of which are irrespective of the hardware platform. And then you can also couple them, which Thierry is going to talk about in his talk, with specialized optimizations directly for certain platforms. So for example, I'll talk a little bit about quantization. We apply quantization to map down to our accelerator, which only supports 8-bit or 4-bit or other variants of quantized integers. Okay, so notebook. Okay, so if you guys navigate to the tutorial site, which is linked from ISCA tutorials, or you can follow this URL. Oh, it didn't, sorry. Let me change my desktop. Okay, cool. All right, so you can follow this URL. If you want to follow along, you're also welcome to just listen on and look at the code too if you're not interested in actually executing it. Yeah, sorry. So it's sample.cs.washington.edu/TVM FCRC. Let me see if I can just blow it up. Let me think about that. Let me just open a gist or something.
If you search for TVM FCRC, the first link will get you here.
And it's also on the ISCA site. It's linked directly. Okay, is everyone good? Does anyone want me to wait? All right, cool. So, all right, we pop back over here really quick. So you can see in the program today, we've actually updated the program recently with links to all of the notebooks that we'll be going over today. You can see they're here. They're written with Notebook NB. Some people like Eddie, because Eddie is working really hard, is going to show you 3 notebooks. I just have one to show today. So here, if you click on the link, let me just do it. So if we open link in a new tab, we'll get a Colab notebook. So we're using this Colab tool, which is a tool built by some people at Google Research for teaching people about machine learning online. The idea here is to have IPython notebooks that, of course, is loading very slowly. Okay. All right, so there's this little button which allows you to open in Colab. This is mostly for the GitHub integration. So we have a little bit, this first bubble here, let me clear all the output first. If you're not familiar with IPython, feel free to ask questions. There are some other TVM people in the room who might be able to help if you want to raise your hand. Yeah, I'm going to zoom in, sorry. I was just looking at the runtime to clear all the cells. View. Oh, it's slightly different than IPython. I'll just go with it, it's fine. Okay, so if you run this first.
Can you make the font bigger?
Yeah, even bigger.
Yeah.
It's just hard for me to see from here. Is that good? Maybe just one step out so we can see a little bit better. Okay, so this first bubble. So right now, you might want to reset runtime. You don't have to necessarily do this every time. This will launch a new image on Google's side. So it should be, oh, unexpected indent. I just typed buffer, sorry guys. What happened? Oh, I must have deleted something. All right, so this should work then. You'll see this running. So this is just TVM needs to be installed, so this is going to download TVM and prep the machine for you to run it. We'll just go through this. If you have issues, feel free to raise your hand, and maybe Josh and Logan, if you guys are around, you can help people. Okay, so just setting up. Give it a second. I think everyone else who's giving the notebooks will probably do this beforehand. I just wanted to show everyone one time so you can see what's going on. Okay, cool. I'm going to run the second one. Awesome. Okay, so these are also written in a way where if you miss what I'm saying, if you forget in a day or two after talking to people at the conference, you can come back and review the materials. We're also recording all the talks today, so maybe in about a week or two, whenever we get the videos back, we'll update the website with the video on YouTube probably, slides, and the notebook. So you should be able to do all this at home. So if you feel like you just want to watch right now and not follow along, feel free to do that too. Okay, so first thing I'm going to do is just import a bunch of software. This is not a very exciting step. And then I'm just going to show you a little bit about working with the IR from a relay level. So the first thing I'm going to do is talk a little about the language, and then we'll drill down deeper into different topics. So I'm just going to show you briefly sort of the high-level concepts of the language. So relay is like a normal, if you're a programming language person or you build compilers, relay is like a normal programming language. The primitive first operation we have is a variable. So variables have types in relay. So you can imagine here we're going to initialize a few of them. The first thing we'll do is just build a variable without a type. This will leave its type unconstrained and will be solved by inference. Then we can specify the data type, for example, which will control this to be an int32. And we can also do things like provide a shape. So if we go through this code right here, we can play it. I can also show, for example, here, if we print x, we can see, for example, that x is a tensor of 10 by 1 with a float32 data type. So you can see here, this is actually the text format, which I'm going to talk a little bit about later. The next important concept in relay is operators. So all of these currently are backed by TVM operations. So all of these will be expanded into TVM IR and then compiled through the normal pipeline. So we can, for example, we can just run this code right here. You can see that if we build a fragment of a program where we say add x plus x, we're going to get out a program that says add xx. So add here, variables written without any prefix in relay are operators. Variables with this percentage sigil are local variables. It's very similar to LVM. And then we'll see in a little bit that global variables are written with an @ sign in front of them. So we can also use operator overloading and many of the other features that we have in Python. So when you write a Python AST, there are many ways to build a relay program today. One way is a DSL in Python. So when you write it like this, you can build a program. You can see the program's identical to the one that we just wrote. Another primitive concept in relay that I'm going to talk about really quick is functions. So this is how we often represent a model. The idea is a model is a function from its input and its parameters to some output. So instead of treating it as a graph, we just treat it more like a normal programming language. Every model itself is a function. So for example, here I'm going to build a function from one argument. So this is going to be the function that takes in a tensor and adds it to itself. Nothing really exciting. So you can see here in the text format that we have a function now which will take in a single tensor of a static type and add it to itself and return it. You can see the return type here is admitted because it's inferred. So we statically know all the type information, but we do inference over the program. The other main concept that I want to talk about before I dive into actual examples is a module. So the packaging of a relay program, very much like LVM, is a module. So you can see here we create an empty module called mod. We're going to create a global variable called fname, which is the name of the function. And then mod is treated has an interface very much like the dictionary. You can index it by a global name, and you can assign a function into it. And then you see here at the bottom when we print the module, you see all the functions. You can now see, because the function has been type checked, we will by default annotate it with all of its type information. So you can see now the return type is tensor 10 by 1 float 32. You can see we have a helpful printer, which I'm going to talk a little bit about, which can annotate information at every expression boundary. So in this case, you can see that the type checking of the return value is actually the return type, and it will print it for you. So that's exactly what this thing's doing. And this is comment syntax in the text format. So now I'm going to jump a little bit into front ends. These are sort of the main concepts you need to map your computation graph understanding directly into relay. We support other things such as control flow, but for the sake of time, I'm just going to kind of keep it simple. We have many more tutorials on the TVM website. So one of the main attractive things about TVM right now is that we have very robust front end support. So there's many frameworks. These are some of the ones I'm going to highlight. So the important ones, ONNX, TensorFlow, Keras, PyTorch, and Cafe2 all have support, including MXNet, which I guess got cleaved when I was hacking this morning. MXNet has the MXNet team actually has been doing a lot of cool features lately. Hai Chen, who's not here unfortunately because he's moving, has been working on some cool features, and there's a lot of AWS people here today who are going to talk about the MXNet integration. So I just used ONNX today as an example of something different because I thought the Amazon people would talk about MXNet. So you can see here is the ONNX graph. It prints out this large graph. These are all the inputs and the parameters and everything. And there's this just massive amount of graph. ResNet's actually a huge model. Like if you visualize in GraphViz, it will sometimes take up like multiple pages worth of PDF just to get the thing visualized. So now you can see, let's just scroll above for a second. So all we did here is we actually took PyTorch's version of ResNet 18. So I'm just trying to show how flexible it is to mix and match things. So we took PyTorch's version of ResNet 18. We then exported it using PyTorch's ONNX export functionality. So this allows PyTorch to take a model and put it in the ONNX format. What this does, though, is by default it saves it to disk, so it saves it in this file, resnet.onnx. If we scroll all the way down, you can see now what we're going to do is we're going to load that ONNX model directly from disk. And then we can call, so Relay has many of these, but it's if you do relay.frontend.from Onyx, from PyTorch, from TensorFlow, there's a huge variety of these APIs that allow you to directly convert. So the only thing we have to do here is the graphs from other frameworks are unannotated with shape information. So we have to provide the shapes of the inputs to be able to recover shape information for the graph. That's sort of a limitation of the existing IRs that we have to adapt with. But what will happen is when you're done, you'll get a Relay program out. So I can run this. You can see that when you print a function in Relay, by default, you get a human-readable version of it. So there's no like reading protobufs or anything. You can actually read the entire program right here. So for example, this generates a module that is a single function called main. Main, in this case, implements ResNet. So you can see here we have all the arguments. There's a ton of arguments. We have a lot of improvements to the printer actually coming, but they're not merged into master yet. But you can see there are all of these, and here's the model. So you can see at every line, for example, that we assign a temporary variable to each operation call. So for example, here's a convolution. And you can see exactly what I said is, the nice thing is that you can get a human readable debuggable output. For example, you can see the type at every single operator call just in a printed format. So instead of needing to go into the Python debugger and ask questions about the shapes of nodes or many things you might have to do in existing graph IRs, you can easily ask any node its type with a single API. So you can see, okay, here's ResNet. It's not very exciting. It's a lot of ReLUs, convolutions, a batch norm. Notice the batch norm. I'm going to show later how we optimize this away for inference, and that's something to keep track of. So I want to talk a little bit about the textual format because I'm just showing you some of the functionality that we support. So I'm going to pick a smaller model now that we're going to highlight on. So this is an MLP, like a really simple multi-layer perceptron model. So we have some models that are baked into the Relay namespace that we use for testing, so you can play around with them. So you can do relay.testing.mlp, get workload, relay.testing.resnet, get workload. So here's the MLP that we have in the Relay testing. So you can see this is much simpler of a model. You can read it in one frame. You can see exactly the same thing here. The types are propagated on the side, but you might think that this type propagation is a built-in feature, but it's actually just the default annotator. So the Python, because we have this philosophy of exposing everything in Python so that people can easily prototype and hack, we have exposed all of this to people, and I'm going to show you right after one more section. Right now, when we print, like for example, if you see this MLP here, we have what we call a metadata section. The metadata section is very similar to the JVM's constant pool or other interchange IR formats where we have data that's not embedded directly in the program. The reason why this is important is you can imagine machine learning. For example, even a reasonably sized model sometimes has hundreds of megabytes of parameters. And if you were to print, let's say, 300 megabytes of parameters, you're not going to get anything out of that. So for example, we don't print constants directly in the program often because it would make it very hard to read, and we want to store them more efficiently, not in a textual representation of them. So we can actually, by default, that is turned off. Currently, there's no constants in this MLP program, so you can't really see. So I wrote this little helper. You can actually see this is an example, and I'm not going to walk directly through it, of how easy it is to write some AST transforms. So I wrote a 4-line function, which is going to take the model, take all the arguments that are currently parameters. So you can see up here, there's a bunch of parameters like the fully connected weight 1, fully connected bias, fully connected weight 2, and so on and so forth. I'm going to put them directly into the program, and then I'm going to print it with metadata on. So what this will do is you can actually see if we run here. Now, oh, I didn't run this cell. So now we can run this one. So you can now see instead of having n inputs that I had before, I only have a single data input here. And all the constants have been inlined into the program. So the way that we reference this metadata about the program is metadata is keyed by type and then by position. So it's essentially just a big flat representation of all the metadata we want in the program. So you can have it keyed by multiple different types and multiple different values of that type. So you can see right now the default text format will encode this as JSON. There are other ways that we could do this. So you can see that there are maps containing constants, and you can actually see the data down here for these things. And this is like the rich format, which has way more text than you might want, and it base 64 encodes the contents of the array. So the idea is this is sort of a packed binary representation for the parameters, and you can serialize this to and from disk and read it back and forth. So this is a way to self-contain, capture the entire model. We also have a parser that can parse this textual format back into a program, like a normal programming language, which is often different than many of these graph IRs, which only use binary formats such as proto-buffers or another serialization format. The final thing I want to show you about the text format is the annotator that I was talking about. So we can actually, when we invoke the printer in Python, you can see right here, I'm going to do this line down here at the bottom that says as text. As text is the helper method. With no arguments, it will convert it into human readable format without metadata. You can see that I turned on metadata here. So show metadata equals true. But I can also pass a callback for annotator, which is a function that will be run on every single expression in the language. So you can see here what I'm going to do is I'm going to use a counter. I'm going to do something really dumb. I'm just going to number every expression with this string. So this I'm using F strings in Python if you haven't seen them. All this does is string interpolate. So I'm going to create a expression number thing, and it will annotate it all over the program. So you can see this is actually a really good debugging tool where you can write a program that automatically runs some code against each expression and gives me some input. And we've really been focused on these tools because we find ourselves spending a lot of time debugging when you're building your compiler. Spend a lot of time in the internals trying to figure out what's going on, debugging passes, trying to read analysis results. So you can see here I've actually annotated the expressions everywhere. So this doesn't produce textually valid format right now because I'm putting inline comments everywhere. But I can change this to output a comment if I want. So you can see I annotate the operator itself with an expression, then I annotate its its arguments, and then so on and so forth, and we get down to expression 16 at the very bottom, which is the entire expression of the body of the program. So you can use this to hack really quick. So we can say hi FCRC. We can just see really quick that it appears everywhere in the program. So we find these kinds of things, like quality of life improvements that don't necessarily have any novel technical aspect to be very useful in developing the tools today. So now I'm going to talk a little bit about executing Relay. And let me just check the time. Okay, we're on time. Cool. So now that we've seen how to write a Relay program, the question is how do I execute them? So we actually have really simple interfaces for quickly deploying a model and getting feedback for it. So I'm going to do the same thing here where I'm going to create an empty module. So you can also run a sub-expression inside of the context of a module right now. So there are 3 different evaluation strategies currently supported in Relay. There's what we call debug, which maybe is a misnomer because it's not necessarily debug in the sense you might think, but it's like a reference interpreter. So the idea is it's a very simple interpreter that is just a very small amount of code that can be easily maintained and audited that implement the semantics of the language. It also does support debugging, and we can use this to quickly get feedback from a Relay program. We can write it up and try it really quick. We don't need any sophisticated compilation to do that. And this debug interpreter, the only cool thing that it does, I think, is it uses JIT compilation. Evaluate, if you pass it a function and no arguments, will return a Python function back to you that you can then evaluate at another time. So if we run here, you can see, okay, everything there is evaluated. We now have a bunch of functions, and you can see that I can now run this down here. So what I'm going to do is we have all the parameters for the model already, because when we make the call to the testing API, we get the parameters, and I can go back and show you for a second. When we get the MLP, as you can see, when we get the MLP out, the testing API provides models with both a set of parameters and the model definition itself. So this is so we can easily try things, assuming we have the whole model definition. Go back down. And the nice thing is that these things work very much like Python functions. So the params are passed as keyword arguments. So I'm using this ** to pass all the keyword arguments. And the inputs are passed like normal positional arguments. So you can see I have the debug MLP, the graph MLP, and the VML MLP. All these are running on different execution machinery and running different steps of compilation even, and have different optimization pipelines, but the interface is identical, and I can experiment really quickly. So you can see that they all produce identical results. And that's all you need to take to run a model. So you can get up and running and run code really, really simply. So the virtual machine is still under development. There's a lot of cool stuff going on in it. If you want to read about it, there's some more details linked directly in here. You can follow our development on the repo. So the final thing I want to talk about before we wrap up is optimizations, which is sort of the bread and butter of this part of the compiler stack. Now I think we have the tools to talk about optimization. So what I'm going to do is we're going to implement a simple constant folder right here in the notebook. So the constant folder is 2 pieces. The first thing we're going to do is we're going to define a simple visitor, which just checks to see whether an expression is constant so that we can see whether it's profitable to evaluate or not. So all this does is there's a visitor that's defined in Python. We inherit from it. We call it superconstructor. By default, we assume all things are constant. The only three cases we're going to consider right now in this constant folder are actual literal constant tensors, operations, which are always constant, and calls, which are only constant if their arguments are constant. And if we're not one of these cases, we're going to say false, and then we're going to just recursively visit the program. So this is like a simple implementation detail that's not actually that important to write in the constant folder. We can expose this, for example, as a simple helper function. Let me run the code up here. We can expose this as a simple helper function, which is going to instantiate the visitor, run the visitor on a single expression, and then return whether it's constant or not. So once we define this, we can quickly do that. With that in hand, we can build the simple constant folder I talked about. So we support another visitor style interface called a mutator. The mutator is actually immutable, but it will produce a new AST from the old AST. So what we do is we rewrite the program from the old program into the new program. The rewriting that we're going to do in the constant folder case is only for function calls. If we see a function call is constant right now, we will evaluate the function call, and then we will substitute the result back into the program. So you can see the way that this happens is we overload a single method in the visitor. We check to see whether the call node that we are getting passed in is a constant or not. We then use the same executor interface that I just showed you a few moments ago to instantiate a relay interpreter. We can then evaluate that call node directly on the interpreter, and then we can take that constant, build a relay constant AST node, and inline it directly back into the program. And that's all we need to do. We can do the same thing I did below. We can write a little helper function which instantiates a visitor, applies a visitor, and reads the result out right here. And then I can show you an example. So we can take an AST. This is a really trivial example, obviously. But I can take one relay constant and another relay constant, so C1 and C2. I can add them together. So this is going to build a program that is using addition. So you can see here that my input expression is the adding of the first constant in the constant pool and the second constant in the constant pool. And then I'm going to output, I forgot to hit run. Now we can hit run again. Now you can see that all I did was I took all the ones, because I used numpy.ones to generate this, these constants. So these constants are just tensors. One's 10 by 1 with all ones. One is 1 by 1 with all ones. And because we support broadcasting, they just broadcast, they add together perfectly, and we get out this result, which is the 2 by 2. Okay. So now that we have a pass in hand, I want to show you a little bit about some of the infrastructure that we can do with passes. We can, for example, take ResNet. I'm getting the ResNet model from the same testing namespace I talked about earlier, including its parameters. And we have a nice abstraction in the pass manager now where we've built passes to be generic functions from module to module. And we have sort of similar abstractions you might find like a layers library that allows you to stick together passes into pass pipelines. So for example, we can do a sequential pass management where we're going to first infer the type. We're going to do simplify inference. Simplify inference removes things that don't need to be there at inference time. For example, batch norm can be turned into just multiplication and division. We can fold away the constants. That's the built-in constant folder. We can eliminate common subexpressions, and then we can apply alter layout transformation, which changes the memory layout for tensors in order to obtain better performance. So we can build a sequential pipeline. Now, in order to apply this, we can build a module. So on this first line, I just build a module where this ResNet module, ResNet network, is the main function. Then we can set a build config. Build config allows us to control, this is similar to putting command line options for GCC or something, allows us to control the op level, what passes are enabled. So here I want to run an op level 3. Then I'm going to set the target. There are more than one way to set the target, but here's one way to do it. So I'm going to use LVM to generate code, and this is going to run on CPU. And then I'm going to apply, just like a normal function, I can apply the module, the pass manager, directly to a module and get a new module out. So it's really easy to compose passes because there's no setup that needs to happen. They all will stick together nice and functional, and so you can build these pipelines, which then can be composed into trees of pipelines. You can search over pipelines. You can run them in arbitrary order. And then so if we run this, you can see now that we get out something that has been optimized. You can see now that there are no batch norms left in this network. Like if you look through the network in the notebook, you'll see there's no batch norms, and that's due to simplify inference, for example, has removed all of them. You can also see that these layout transforms appear all over in the program. This is explicit operations which do a layout transform on the memory before doing an operation to obtain better performance. And I think the Amazon people will probably talk about this later today. They did much of this work. So Finally, we can use passes just like normal functions in the AST, but we can also lift single expression transforms to be a pass themselves. So we can take the same function that we just defined above a few lines ago. We can wrap it in this decorator in Python, relay.transform function pass. We can set its op level, and we can set its name, and now it will be official pass in relay that we can get access to. So that's all we had to do that. You can see we can modify the pass pipeline that we used before to just contain myfold constant instead of the built-in one. And now we can run it, and we get the same result out. So what I want you guys to take away from this is just that the pass manager is super easy to build infrastructure around configuring different compiler passes. For example, we have different ones for Vita, what Thierry is going to talk about, for CPU, for GPU, for the VM, for the graph compiler, and so on and so forth. With the final thing I'm going to wrap up, I think I have a few minutes left, is I'm going to talk a little bit about a quantization pass that we built. So one cool thing that we've done using the pass framework is that we built not just like a single quantization set of operators that we then have to use, but an automatic quantization framework. Some people I've talked to have said, like, why do you want to do automatic quantization? Like, why don't you just let the model users define when they want to quantize? And to clarify, quantize is the process of taking a data type, let's say float 32, and reducing it to 16-bit, or maybe going from float to fixed num, like integer, or maybe in the future, things like posits or other data types that we're interested in. So the way the quantization framework works for us is actually, the reason we want it to be automated is certain hardware devices require quantization. So it's like if you can't perform it, you're not going to run anyways. And we want it to be easy for users to have a push-button way to get to certain devices for classes of models. So quantization in our framework begins by taking, we've simplified the presentation of the program here a little bit. We can imagine a pipeline where we take a convolution with its inputs, we then perform batch norm, then we perform ReLU, and then we find another convolution. And these kinds of pipelines are very popular in vision models. For example, ResNet and Inception have many pipelines like this. The idea is that we want to eventually change the convolutions to run, let's say, in the int8 space. So the way that we're going to do this is we're going to perform, first we're going to do an annotation pass. So what we're going to do is anywhere that we are going to detect areas that are eligible for quantization, we're going to insert simulated quantize, big performance increase with no data-aware tuning. Sometimes, for example, you only lose less than 1% of accuracy. So there's a lot of different strategies, and that's really why we built this framework, is that you can overload and play with how different quantization strategies and try different techniques out. So then what we've done is after realization, we will take these simulated quantized operations, we will turn them into a sequence of operations that actually just convert from, say, float 32 to int8 by scaling. And then because we can do operator fusion for arbitrary operators, we just push the conversion directly into the operation itself. And now we don't need to write new quantized convolution or new quantized addition or new quantized multiplication for every variant. So a cool thing that can happen is you can actually control, like in this pipeline, we're doing inputs in I8, but we're accumulating in I32. On ARM has a 16-bit accumulation instruction. It's actually really profitable performance-wise to use 16 bits instead of 32. And there's some results from Zihang, who's not here today, we can talk about offline, where he's done a lot of these experiments. And you can find some of the details in our archive paper on Relay. So I'm going to show you how to use it really quick. I don't have time, unfortunately, to show you how to extend it and hack on it right now. I think I only have 5 minutes left, 3 minutes left. So I'm going to do the same thing. I'm going to get the ResNet workload from the testing namespace and its parameters. And it's going to take a second to run. So you can see we have the familiar ResNet here. It's got all of its parameters inlined. But this is actually after quantization. So if we, here we go. So you can see here actually that the convolutions now, their types have changed to int8. So we've actually just done this quantization, and you can see exactly the set of operators I'm talking about. So this multiply, round, and clip are actually what manifests the scaling from float down into int. And because we can do fusion in long chains of operations, we can just coalesce them into a single set of loops at the low level when we generate code without having to write new low-level operations. And you can feel free to come talk to us. I wish I had a little bit more time to cover this. I just want to give you a taste of what's possible with Relay today. And I have a couple more things to talk about before we finish. So I'm going to go over this a little bit quickly. But another interesting thing that we support in Relay is heterogeneous execution. So what we can actually do is, this is another me doing a path on a slide kind of thing. We want to, for example, let's say we want to schedule all convolutions on GPU. All we need to do is rewrite this much code to try a new scheduling strategy. So what we're going to do is we're going to do the same thing we did before. We're going to write a simple visitor. the main critical piece of this visitor, if we detect that you are doing convolution, we can attach this annotation, and we make heavy use of these annotations in Relay. This is essentially a special function call, if you will, which will tell us metadata about an expression. So in this case, relay.annotation on device will contain an expression, say a convolution, and it will tell us to schedule that convolution on the GPU. And we will then, when later on in the compilation pipeline, insert all of the memory operations which are required to transfer memory in between devices and do the synchronization. So it's really easy to write this. You can just run this, and now we have a path that will actually schedule on GPU, and you can then run through the pipeline. And just for the sake of time, I'm going to skip ahead. You can check this out in the notebook. But when we're done, we can now have a ResNet that runs, and you can see, I'll just show you really quick. On device, we got to scroll a little bit lower. You can see, for example, that there are copies inserted before and after operations, which will do the memory synchronization. The last thing I want to show you is one cool little thing that we did where we built an ahead of time compiler. So there's an open source project that was written by, started by me and then finished by one of my undergrads who's here in the audience. And we built a compiler in a few weeks to just compile Relay directly to C++. So this is the kind of stuff that we're interested in, is the IR can be really useful for people building your own compiler, but just reusing the components that we have today. So what I'm going to do here is I'm going to take the MLP. We can just import this library called AOT, and the code is linked in the notebook. And you just call compile, and it will generate C++ code. And then the cool thing about this is that it will take the C++ code, compile it to a shared library, link it into Python for you, and now you have this handle to it that you can call just like a normal function. So if you see CMLP, this is actually code that has been compiled via C++, dynamically linked in, and now you can invoke. And this will even support cross-device execution. So that C code can be scheduled on GPU, and it will do CUDA launches, and it will be running on CPU. And this is just like a few weeks of hacking before deadline for us to build proof of concept. And then the final thing I want to close with is, all of this infrastructure has a lot of useful value, and it's, there's people building awesome service in Amazon that they're going to talk about today, but other frameworks are also really interested in this. So some engineers at Facebook in the last few weeks have been using TVM as a backend for PyTorch, and they have really exciting performance results. There's another blog that was written by our friend Bram, who has done all this work at Facebook, and you can see actually that Relay's here in green, TVM Relay, you can see dramatically improves performance for ResNet, which is, again, one of the most optimized models. So you can see, imagine if I have a less traditional model, that I might gain even bigger performance gains over PyTorch's standard JIT. So you can see, actually, here's a little snippet. I didn't have it built in here because right now it's on a fork of TVM, but you can see compiling a small Relay program right here, this add directly down to Relay, and so they show how to use the machinery to get a Relay program out of your Torch program. So if you're interested, I linked to Bram's blog post here. You should go check it out. It's really interesting, and he's been doing some really cool work. And with that, I will open it to questions for maybe a minute or two, and then we'll go for the morning break. Sorry, Eddie, sorry, I jumped the gun. Does anyone have any questions? Or yeah. So it depends on how, maybe T&C actually has a better answer to this question, and because they did most of the work, I just wanted to demonstrate it today. But right now, if you want to change, for example, like the bit width or the data type, it's very easy to do. Like the 16-bit, 32-bit thing was done in like an hour or something. Like most of the work was running the experiments actually, not even modifying the compiler. If you have an exotic data type, which Gus's going to talk about today, might be a little bit work. And if you want to support new operations, Thierry's done it recently. Like maybe T&C can say a few words, but.